Hello everyone, Simon here. Welcome back to our Learning Neuroscience and Psychology from Gemini series. It's an awkward name. Anyway, so in this video I want to talk about emotions and what happens inside your brain when you have different emotions. And I found this. This is a Plutchik emotion wheel. So we have a systematic um, categorization, right, of emotions, human emotions. Let's start with happiness here. All right. So we're gonna ask Gemini. Um, what should I ask him? I want to understand what happens inside the brain when humans feel different emotions. And also how it affects the body. Let's start with happiness. Let's say someone, let's say a person is successful at work or school, and that makes them feel happy. What's going on? What's going on in the brain to produce that feeling? And how does that affect their thoughts and their bodily functions? Okay, let's see what Gemini says. Success-induced joy. When you experience success, whether it is a high grade on an exam or a promotion at work, your brain undergoes a reward cascade. It is not just a fleeting feeling, it is a systematic biological event that shifts your three-story house into a state of growth and relaxation. Here is the step-by-step breakdown of achievement happiness. I mean, that's only one type of happiness, apparently. I guess there's other types of happiness too, right? The spark, the reward circuit. The moment you realize you succeeded, your prefrontal cortex, the CEO, sends a signal down to a small but powerful area in the limbic system called the ventral tegmental area, VTA. Let's find where that is. Ventral tag, oh, the brain, tegmental area. What the hell's that? What are we looking at? This? The mesencephalon. It's very deep. So happiness is very deep in the brain. We can say that. Interesting. So you notice that the happiness is right on top of the brainstem, whereas the fear and the anger is further out to the side. So the positive reward is closer to the center of the brain. Interesting. All right, the dopamine flood. The VTA releases a surge of dopamine into the nucleus accumbens, the brain's pleasure center. Uh, do we remember where that is? Nucleus. Uh, um, hold on? Did I spell that wrong? ACCUMBNS. Nu hmm, did I spell that wrong? Oh, there it is, at the bottom. Okay, so it sticks the dopamine into there. The feeling, this is the high of success. It's an energizing I did it feeling. Evolutionarily, this reward system exists to encourage us to repeat behaviors that are good for our survival, like gaining status or resources, right? So when you recognize that you've done something positive to yourself, your brain releases the pleasure chemical to reward you for doing something right. And then the stabilizer, number two, serotonin and pride. While dopamine provides the spike of excitement, serotonin provides the glow of satisfaction. Social status. Serotonin is often linked to our sense of social importance and belonging. When you are recognized for your work, your serotonin levels rise. The feeling. This is the calm, steady feeling of I am capable and I belong here. So this is confidence, I guess. It balances out the dopamine so you don't stay in a state of hyperarousal. Right, so the instant reward and then the sense of confidence. Three, impact on thoughts. So broaden and build theory. Happiness physically changes how your cerebral cortex processes information. Cognitive flexibility, when you're happy, so I guess that's when your serotonin levels are high, your prefrontal cortex becomes more flexible. You are better at big picture thinking and creative problem solving. Fascinating. So the flood of chemicals changes how your brain thinks. It becomes more flexible, more like out of the box thinking. The feedback loop, success breeds success because your brain enjoyed the dopamine hit. It begins to prime your motor and sensory lobes to look for the next opportunity to succeed. You become more approach-oriented rather than avoidance-oriented. Right, so I guess it also inhibits your fear, right? If you're switching away from avoidance. So it switches on the approach. Number four, impact on the body, the parasympathetic shift. When the brain signals success and safety, the hypothalamus, the thermostat, tells the brainstem to switch the body's operating mode. Right, so the nervous system, it activates the parasympathetic rest and digest. Why? The threat of failure is gone. The body can now recover. So your body relaxes and you can rest more easily. Your muscle tension in the shoulders and jaws decreases. You no longer need to be armored against stress. So your muscles relax. Your heart rate variability increases, become more rhythmic. It signifies a state of emotional regulation, right? So your heart rate calms down. Your immune system, your cortisol levels drop. Cortisol levels drop, natural killer cells activity increases. The body moves energy from emergency response to long-term maintenance, right? So your whole body relaxes and it switches to the safe mode, right? You assume that you are safe, and so all the things you need to do to guard against dangers shut down. The happiness summary table. I don't think we need those tables there. Right, so it changes your whole body. So the dopamine is the short-term high, and then the serotonin is the long-term comfort. Very interesting. All right, let's move on to the next one. So this is admiration, trust, and acceptance. So this is like social bonding. Um, so this was what did Gemini call it? Achievement happiness. Achievement happiness. All right. So the next emotion I want to explore is I guess like social attachment or love. Sure, let's just call it love. Like let's just call it what it is. Admiration, trust, let's say yeah, that's love. Is love. Let's say a person is with someone they have a deep social and emotional connection with what is how does the brain respond, and what is the effect on the body? I I would guess that some of the serotonin glow. Let me not preempt it. Let me just let Gemini answer the question, right? Love is perhaps the most complex chemical cocktail the brain can produce. While pop culture often points to the heart, in neuroscience, love is a sophisticated interaction between the reward system, dopamine, and the social bonding system, oxytocin, my bad. Oxytocin. When you're with someone you have a deep connection with, your brain isn't just feeling something, it's physically rewiring its priorities. Like, it's so cool, right? Your brain physically changes, the chemicals change, and your brain changes, right? The attachment system, oxytocin and vasopressin. In a long-term deep connection, the star of the show is oxytocin, often called the attachment hormone or the cuddle chemical. Production, it is created in the hypothalamus and released by the pituitary gland. I don't think the gland is in the brain diagram. The fear mutant, one of the most incredible things oxytocin does is physically deactivate the amygdala. Amazing. So, so like colloquially, you are unable to be angry at somebody you love. You know, like, oh, you did something wrong, but I can't get mad at you because you're so cute. Like that feeling. You know they did something wrong, but you can't get mad at them. Like literally in your brain, the oxytocin is deactivating your amygdala. So it's shutting down the part of your brain that deals with anger, right? So it's not like just a feeling. Your brain is actually unable to be angry when you are in love. It effectively turns down the volume on fear and social anxiety. This is why being with a loved one makes the world feel safer. It feels safer. Is it actually safer? Probably not, but it feels safer, right? Vasopressin. This is oxytocin's brother chemical. It is linked to long-term commitment and protective behaviors. It helps the brain tag a specific person as a permanent priority. Right, so this is attachment. And then there's the reward system, addicted to a person. Deep love also uses the same machinery as addiction. The ventral tegmental area, VTA, floods the nucleus accumbens with dopamine. So again, the dopamine, remember with the success, the dopamine spike is the pleasure. So when you're in love, the same kind of pleasure is taking place. The craving, this is why you feel a pull towards that person. Your brain has associated their face, voice, and scent with a massive reward. The activation of judgment. Interestingly, when looking at a loved one, the prefrontal cortex, the logic center, actually shows reduced activity. You stop thinking. This is the biological basis for love is blind. Your brain intentionally suppresses its critical judging faculties to strengthen the bond. So when you're in love, you stop thinking, right? Like you stop critical thinking and you're just going along with the feelings. Like you're not actually logical at all. So you're unable to get mad, you're unable to be scared, you're unable to think straight. You're just drawn to them, right? You're just addicted to it. It's just a dopamine spike. The body, the vagus nerve, and heart-brain connection. Love isn't just in your head, it travels through the vagus nerve, the longest nerve of the autonomic nervous system, which connects the brainstem to the heart, lungs, and gut, so it affects your whole body. The vagotone, deep social connection increases vagotone, which helps the body transition into a parasympathetic state, rest and digest. So similar to the achievement happiness. You relax, you rest. The warm glow. This is the literal feeling of warmth in your chest. It is the result of the vagus nerve signaling your heart to slow down and your blood vessels to dilate. Wow. Your heart slows down, your blood vessels dilate, you literally feel warmer. Biosynchrony. Studies show that when two people with a deep connection sit near each other, their heart rates and breathing patterns actually begin to synchronize. Their nervous systems begin to hum at the same frequency. Very interesting. Very interesting. So it shuts down the amygdala. It dampens the cerebral cortex. So it dampens the prefrontal cortex. Alright, so this is just a summary of what we had before. Uh, it mentioned briefly about like drugs and addiction. You mentioned addiction just now. You mentioned addiction. Um, how does addiction work? Is it uh dopamine out of control? Is it the dopamine getting out of control? Let me just ask about addiction briefly. You've hit on the most important distinction in addiction science. It isn't just about too much dopamine, it's about the hijacking of the brain's survival machinery. In a healthy brain, dopamine is a teacher. It says the meat was great, remember how you got it so you can do it again. Okay? In addiction, the substance or behavior doesn't just teach the brain, it screams at it, forcing the brain to prioritize the drug over everything else. Food, safety, and even love. The hijacked reward pathway, as we discussed with happiness, the reward circuit, the VTA, and the nucleus accumbens, is designed to reward us for survival-based behaviors. Natural rewards, eating a good meal might release 1 unit surge of dopamine. The hijack, drugs like cocaine or methamphetamine can release 10 to 100 units of dopamine almost instantly. So it's like 100 times of your natural happiness. The brain is not built to handle that much volume. It's like plugging a 110-volt toaster into a 10,000-volt power line. To prevent itself from burning out, the brain takes drastic defensive measures. 2. The brain fights back, tolerance and downregulation. When the brain is flooded with dopamine, so too much dopamine, it tries to restore balance, homeostasis. It does this in 2 ways, shutting down the receptors. It hides the dopamine, locks the receptors so the signal can't get through. Producing less dopamine, it stops its own natural production. So it tries to maintain like a balanced level of dopamine. It produces less of its own dopamine, and it also reduces the sensitivity to dopamine. The result, this is tolerance. Now the user needs more of the drug just to feel normal. Because natural rewards like a sunset or a conversation only releases a 1 unit surge, and the brain has hidden its receptors, the person can no longer find joy in everyday life. This is called anhedonia. Hedonism is happiness, and hedonia means a lack of happiness, right? Uh, Interesting. So the drugs flood the brain with dopamine. The brain tries to compensate by lowering its sensitivity to dopamine. And so now in the absence of drugs, the person is unable to feel happy because the sensitivity to dopamine has been reduced. The gauge effect, the CEO loses control. As addiction progresses, it physically changes the prefrontal cortex, our CEO. In an addicted brain, the connections between the executive penthouse and the limbic living room weakens. Well, because it's trying to reduce the dopamine inflow, right? And so it's weakening the connection between the dopamine production and the prefrontal cortex. The brake system, inhibition, begins to wither away, while the go system, the craving, becomes hypersensitive. Does it? This is why people with addiction often say they want the drug even though they no longer like it. The dopamine system, wanting, is screaming, but the opioid system, liking pleasure, has been blunted. Mm. Wanting versus liking, the great distinction. One of the biggest misconceptions is that addiction is about chasing pleasure. Modern neuroscience shows us that it's actually about incentive salience, craving. So the liking versus the wanting, chemical. Endorphins and opioids is the liking. Dopamine is the wanting. Pleasure, satisfaction is the liking. Urgency, craving is the dopamine. Right, you crave it, you get it, and then you feel the pleasure, supposedly. But when you are addicted, you only crave, you don't really feel pleasure anymore. Action is enjoying it versus seeking the next hit. In addiction, the liking system often breaks down, but the wanting system stays on high alert. Right. So this is why an addicted person might be miserable while using, yet feel a physical, uncontrollable need to continue. That sounds horrible. Why willpower isn't enough. Returning to our course theme, if the physical hardware of the prefrontal cortex is compromised, asking someone to just use willpower is like asking someone with a broken leg to just run a marathon. The physical mechanism required to exert that will is functionally damaged. Isn't that interesting? They physically can't do it. The path to recovery, neuroplasticity. The hopeful news is that because the brain is plastic, it can heal. If the hijacking substance is removed, the brain slowly begins to regrow those dopamine receptors and strengthen the connection back to the prefrontal cortex. It's a slow process, often taking months or years, of retraining the CEO to take charge again. So this is rehab, right? Rehab is you have to be off the drugs for an extended period of time, and eventually your brain will grow back and change back to how it was before, eventually. But it takes months or years. So it takes a long time to do it. Fascinating. Fascinating. Okay, let's get back to emotions. The next thing is terror, fear, or apprehension. Terror. Next, I want to explore fear. Um, let's say a person who has a fear of spiders sees a spider. What happens inside their brain? And how does it affect their body? Fear is the brain's most efficient survival mechanism. Efficient. Efficient means it's fast and it's effective, right? When a person with a phobia sees a spider, the brain doesn't think, it reacts. This process happens through what neuroscientists calls the two-track system of fear. Mm. Uh, the low road, the instant jump. Within milliseconds of the light hitting your eyes, the information travels to your thalamus. Before your conscious brain even knows what the object is, the thalamus sends a low-resolution snapshot directly to the amygdala. You're not even processing. Like your op your occipital lobe is not processing. Your prefrontal cortex is not processing. It's just going straight to the amygdala, straight to the thalamus, straight to the amygdala. You're not even thinking about it. The reaction. You jump back or scream before you've even consciously identified the spider. That's amazing. You don't even need to think. The logic, evolutionarily, it is better to jump at a shadow that looks like a spider than to wait and be bitten by a real one. Yeah, so you react first and then think later. Because it should be dangerous. Like if it might be dangerous, it's better to avoid the danger. And then the high road, the conscious terror, a split second later, the visual information travels to the occipital lobe and then to the prefrontal cortex, right? So afterwards, the signal arrives. The realization, your thinking brain confirms that is definitely a large spider. The loop. For someone with a phobia, the prefrontal cortex fails to quiet the amygdala. Instead, it sends signals back that reinforce the danger, creating a loop of panic. All right, so you just have a feedback loop. 3. The body under siege. This is the sympathetic surge. Once the amygdala sounds the alarm, the hypothalamus, the general, initiates the sympathetic nervous system, your fight or flight mode. It triggers the adrenal glands to dump adrenaline, epinephrine, and norepinephrine into your blood. Bodily function: the pupils dilate to let more light and to let in more light and detect movement better, so you see better or you see more directly. Your lungs, your bronchial tubes dilate to take in more oxygen for a quick escape. So like you see better, you breathe more, your heart rate and blood pressure skyrocket to pump oxygenated blood to your leg muscles, right? So your heart goes into overdrive, your blood pumps more quickly, your digestive system shuts down, dry mouth, energy is diverted away from digestion to survival. So this is like the knot in your stomach, and you get a stomach ache because like you're taking the blood away from the digestive system to the rest of your body. Your skin becomes pale or goosebumps. Again, the blood is pulled away from the skin to the muscles. So all the blood is directed to the muscles so you can run faster. That's crazy. So that's adrenaline. It does all of that to your body very quickly. We have an image there. Why phobias are different from normal fear? I guess I should ask about normal fear too. In a normal fear response, once the spider moves away or is removed, the parasympathetic nervous system, rest and digest, kicks in to calm you down. However, in a phobia, the librarian, the hippocampus, has stored such a powerful negative file on spiders that the brain stays in a state of hyperarousal. Even after the spider is gone, the person may remain shaky, sweaty, and hypervigilant for a long time. Right. We don't need to talk about Gage. Um, oh, I've reached my limit for thinking models. So I want to ask, so that was a phobia. What about a sense of dread? Is that different from the acute phobia response? Uh, let's say someone is scared that there might be something in the dark. Uh, hold on, what am I doing? Might be scared there might be something in the dark, but hasn't actually seen anything scary. Okay, let's see what Gemini says. And we switch to fast mode, so it's going to be slightly less intelligent. This is a fantastic distinction to make. In neuroscience, we distinguish between fear, an acute response to present danger like a spider, and anxiety, spread, or dread, a prolonged response to uncertain or potential threat. When you're staring into a dark room and feeling creeped out, your brain is performing a very different type of calculation than when it sees a spider. The ambiguity circuit. While acute fear is driven by the amygdala, a sense of dread involves a nearby but distinct structure called the BNST, bed nucleus of the stria terminalis. Bed nucleus, it's very specific. Bed nucleus of the stria terminalis. Uh, no. Basal ganglia. Hold on. The amygdala is there. Basal ganglia and amygdala. I'm not sure where that is. BNST, I don't think you'll find. If I just type in no, it won't. Bed nucleus. No. Basal nucleus? I'm not sure where that is. Anyway, the amygdala is the panic button for things that are here right now. The BNST, bed nucleus of the stria terminalis, is the surveillance center for things that might be there. When you're in the dark, the BNST keeps your brain in a state of hypervigilance. It doesn't trigger a full fight or flight explosion, but it keeps the system on simmer. You aren't running yet, but you are poised to run at the slightest sound. Right, so you're vigilant, but you're not actually scared yet. The conflict of the CEO. Dread is essentially a conflict between different parts of your prefrontal cortex. The rational CEO, lateral PFC, says statistically there is nothing in this hallway. You are in your own house, relax. The imaginative scout, the medial PFC. So the lateral is at the side, the medial is the center. The medial PFC says, yes, but what if the door was left unlocked? What was that creak? Because the threat is invisible, the CEO can't provide a stop signal to the amygdala. In the spider example, once the spider is gone, the threat is over. In the dark, the threat is the unknown. So the brain can't find a clear signal to return to a rest state. The body, the long burn. Because dread is a marathon, not a sprint, the bodily effect is different from the sympathetic surge of a phobia. Muscle tension. Instead of a sudden jump, your muscle stays clenched or rigid. This is why you feel sore after being tense for a long time, right? So your muscles tense. It's like it's a defensive action, right? You tense up to kind of you're prepared for somebody to hit you, and so you're tensing up. But nobody hits you, so you just tense for a long time. Scanning behavior. Your eyes move rapidly. Saccades and saccades, and your hearing becomes hyperacute. You might perceive a normal house noise, the fridge humming, as a threat. Right, so your senses become heightened. The cold feeling. While acute fear can make you feel hot and sweaty, dread often involves a chill. This is caused by prolonged vasoconstriction, your body pulling blood towards your core because it anticipates and needs to protect its organs. Fascinating. So it's a slightly different response, but your body is vigilant. It's not active yet, but it's vigilant. Uh, alright, we don't need to look at that. Okay, so we got terror and apprehension. We got both of those. Great. So amazement, surprise, and distraction. Um, what should we look? Amazement or surprise? Next I want to explore surprise and amazement. Uh, let's say a person is, at a circus show, and they see a performance that they never imagined was possible. They are surprised and amazed. What is happening inside their brain and body when they experience this? Surprise is often called the reset button of the brain. It is a transitory emotion, A bridge between your current state and a new realization. When you see something impossible at a circus, your brain experiences a massive prediction error, which forces it to stop everything else and pay attention. Right, so like something is happening that you did not predict, or it's different from what you predicted. The prediction error, cerebral cortex, your brain is a prediction machine. Based on your life experience, your frontal lobe and hippocampus have built a model of how physics works. For example, humans cannot flip feet 3 times in the air and catch a bar. The mismatch. When the acrobat performs the impossible feat, your brain detects a massive gap between what is expected and what it saw. The P300 wave. Within 300 milliseconds of the surprise, a huge burst of electrical activity, the P300 wave, ripples across your cortex. This is the brain saying, stop the presses, update the files, reality is not what we thought. That's incredible. So like the wave, what it does is it stops everything else and it restarts the brain. So it's like a quick reboot. So it clears your mind of everything else that was going on before, and then you focus on this new thing that you just saw. Right? So this is what this is. The freeze and the orienting response, the brainstem. Before you cheer, you usually freeze. This is the orienting response. Interruption. The reticular formation in your brainstem instantly interrupts all other thoughts. So again, like it's stopping the thoughts, it's resetting. When you're surprised, your brain just resets. Let's see, the reticular formation. Wait, there's no reticular formation. What was it? Not sure, but probably the part that communicates, right? Sensory opening. Your eyebrows arch and your eyes widen. This isn't just a facial expression. It physically expands your visual field and lets more light in. While a sharp intake of breath, the gasp, provides a burst of oxygen to help you process the new information. Amazing. Right, so you breathe in, open your eyes to look at this new thing. The all cascade, dopamine and opioids. If the surprise is good, amazement, the brain rewards you for learning something new. Dopamine burst, the VTA floods the brain with dopamine. This makes the surprise feel thrilling rather than scary. Endorphins, if the amazement is profound, or the brain may release endorphins and oxytocin. This creates the chills or goosebumps you feel during a powerful performance. The small self effect. Interestingly, during moments of intense amazement, activity in the default mode network, the part of the brain associated with self-talk and me-centered thinking, decreases. You lose yourself in the moment. So this goes along with the previous thing, right? So your brain resets, it quietens down, everybody shuts up and focuses on the thing, right? So even the part of the brain that's you thinking about yourself, that part also quietens down and you focus on the thing that is surprising. The body, the mixed state. Amazement is unique because it combines elements of both the fight or flight sympathetic and rest and digest parasympathetic systems. Oh, that's strange. The heart rate, brief deceleration, then acceleration. The heart stopping moment followed by a rush. Right, so your heart stops and then starts again. The skin, piloerection, goosebumps, a physical shiver of excitement. Breathing, sudden sharp intake, gasp. Breathe apnea, holding your breath, followed by rapid breathing. So you're breathing in, taking in more oxygen, vocalizing. Involuntary sounds, whoa or oh. The brain bypassing the language center for raw expression. So this is like your monkey, the monkey part of your brain. So when monkeys are surprised, they vocalize to tell the other monkeys to look at the thing as well. So the social part of your brain automatically signals your surprise to anybody else near you, and when they hear you grunting, they look at you They look at what you're looking at, and then they also focus on the thing. So this is like a social adaptation. When you see something surprising, you immediately vocalize to let the other monkeys know. Uh, we don't. He keeps Gemini keeps trying to conclude. We don't need to conclude. All right, let's move on. So that is surprise and amazement. Next, we have grief and sadness, pensiveness. Let's talk about sadness. Let's talk about sadness next. If a person hears news that someone they know has passed away and they feel sad, what is happening inside their brain and body? Sadness, particularly when triggered by loss, is one of the most metabolically demanding states the brain can enter. Unlike fear, which is an explosion of energy, grief-related sadness is a withdrawal and processing state. It shifts the brain from doing to reflecting. Interesting. Here's how the brain and body responds to the news of a loss. The immediate shock, the thalamus and the ACC. When you hear the news, the information is processed by the thalamus and sent to the anterior cingulate cortex, the ACC. And anterior cingulate, that one. Why did I cut the brain in half? Can I not cut the brain in half? So it's right in the middle there is the cingulate cortex. Cingulate cortex. The social pain center. The ACC is fascinating because it is the area of the brain that processes physical pain, like a broken leg, and social pain, like a broken heart. So physical pain and social pain is the same pain inside your brain. Physical sensation. This is why grief literally hurts. The brain uses the same neural pathways for emotional loss as it does for physical injury. This can manifest as a heaviness in the chest or a knot in the throat. Alright, so you immediately causes you pain. The search for the missing connection, the hippocampus. The hippocampus, the librarian, begins to work overtime. Cognitive dissonance. Your brain has years of files that say this person is alive and part of your world. When you hear they're gone, the hippocampus struggles to reconcile the new information with the old files. Ruminative thinking. This leads to rumination, where the brain constantly replays memories of the person. It is the brain's attempt to re-index its reality. Alright, so you feel pain, and then you go through your memories to try to figure out the difference. Right, trying to sort through your memories versus the new reality. The chemical drop, the low dopamine state. When we lose someone we love, the brain's reward system, which we talked about in the love section, experiences a massive crash. Dopamine and oxytocin depletion. The hit of joy or comfort you usually get from that person is suddenly gone. Oh, that sucks. The gray world. Without sufficient dopamine, the prefrontal cortex struggles to find interest in other things. This is why food tastes bland, hobbies seem pointless, and the world feels gray. Right, so when you're sad, all the pleasure chemicals decrease. And so then nothing feels good, right? Everything feels pointless. But why? Like, why does it do that? What is the... Like, this part, okay, understand that. Hmm. The body, the vagal happiness. While fear activates the fight or flight system, deep sadness often involves a complex mixed state or an overactivation of the parasympathetic nervous system, especially the vagus nerve. The immune system, suppression of T cells. You become physically more susceptible to getting sick. The broken heart effect. Why would that? Because look, why would evolution select for this? What evolutionary advantage does this confer? Does this confer? Your metabolism, high oxygen consumption. Despite doing nothing, you feel exhausted. The brain is burning massive energy processing the emotion. It's interesting that it's such a metabolic load on the body to be sad. Tear glands, activation of the lacrimal system. Emotional tears contain higher levels of stress hormones, like ACTH than onion tears, suggesting crying is a physical way to dump stress chemicals. Okay. Muscle tone, hypotonia. You feel slumped, heavy, or unable to move. Reduce tension. Hmm. The anatomy of sadness. All right, this is the same thing as before. Anterior cingulate processes the sting or physical ache of the loss. Hippocampus replace memories to try to understand the new reality. Prefrontal cortex becomes foggy as it struggles to plan a future without the person. Vagus nerve signals the body to shut down and conserve energy. Lethargy. Is it protective? Like your body slows down and you go back to I guess like the effect of this is your brain is going into the overdrive, trying to replan to like like to go over your old assumptions and try to figure out a new plan, right? Try to figure out what to do without this person. And until you figure it out, your body it tells your body to stop doing stuff while you make a new plan for what to do next. And this is sadness. I guess like all kinds of loss and sadness and disappointment has a similar effect of making you like think through what you need to change. And your body slows down while you do that, right? Uh, Fear, loathing, and disgust. Disgust. Boredom? Not no, not fear. Boredom, disgust, and loathing. Boredom, disgust, and loathing. Mm, Next, I want to explore loathing, disgust. Let's go for the easier one, right? Disgust. Um, let's say a person comes across unexpectedly, unexpectedly comes across rotten food. I mean, we can talk about racism. I don't know if we should talk about racism. Let's not talk about racism for now. Let's talk about rotten food. Uh, uh, what is the brain and body response to that? Disgust is often called the behavioral immune system. Its primary job is to act as a barrier between your body and pathogens, toxins, or parasites, or people you don't like. Unlike fear, which tells you to run away, disgust tells you to keep it out. When you encounter rotten food, your brain initiates a rapid-fire sequence of rejection maneuvers. First, the insula, the core of disgust. If the amygdala is the home of fear, the insula, specifically the anterior insula, is the home of disgust. So let's just look this up. The insula is there, right? Disgust, especially the anterior. Um, this area is tucked deep inside the folds of the brain between the temporal and frontal lobes. Yeah, so right there. The sensor. The insula receives signals from your primary senses, smell and sight, and immediately evaluates if the object is contaminating. Scientific studies have shown that racism triggers disgust. So, I mean, I'm not going to ask about racism, but just keep that in mind. So, seeing rotten food and seeing a certain skin color that you don't like is a similar response. The physical mirror. Interestingly, this insula is also responsible for introception, your awareness of internal bodily states. This is why the emotion of disgust feels so intensely physical. The brain region that processes the idea of rotten food is the same one that monitors your stomach. So when you see rotten food, you also feel it feels the same as having actual bad food inside you. The rejection reflex, the brainstem, as soon as the insula sounds the alarm, it sends signals to the medulla in the brainstem to trigger the gag reflex. The face, you pull the disgust face, wrinkled nose, curled upper lip, and narrowed eyes. Right? The logic, wrinkling the nose reduces the amount of air and foul scent particles you inhale. The curled lip is the first step in spitting or vomiting reflex to ensure nothing enters the mouth. The vagus nerve, the brain sends an urgent message to the stomach via the vagus nerve to decrease gastric tension and increase upward pressure. This is the nauseous feeling. So like you might start throwing up. So decrease gastric tension and increase upward pressure. So your stomach is literally pushing up, and this is like you're about to throw up. The contamination logic, the cortex, while the basement, the brainstem, tries to make you vomit, the cerebral cortex handles the logic of contamination. The law of contagion. The brain treats the rotten food like a magical source of evil. If a rotten grape touches a clean apple, your cortex decides the whole apple is now rotten. Well, there is some logic to that, because sometimes, contagions do spread. The hippocampus, it creates a flashbulb memory of the location and smell of the food so you can avoid that specific area or type of food in the future, a phenomenon known as taste aversion. So it very quickly remembers the disgusting thing as well. Wow. I mean, this is your body avoiding danger, right? Avoiding harm. The body, the quiet revulsion. Disgust has a very different profile than the pumping heart of fear or anger. Your heart rate decreases, a sinking feeling rather than a racing heart. Digestion, salivation increases, stomach rhythm disrupts. Nausea and butterflies of the unpleasant kind. Your skin, a slight drop in temperature. Skin crawling or the creeps. The immune system, immediate brief spike in oral inflammatory markers. The body prepares for a potential infection before it even happens. That's crazy. You see something disgusting and your immune system is already activated. Your immune system is activated just by seeing and smelling the disgusting thing. Wild. I mean, it makes perfect sense because, well, maybe you're gonna get some disease from this disgusting thing. Right? It makes perfect sense, but it's amazing that right? It just does it automatically like that, right? But no, it makes perfect sense. Ah, that's so good. This is slightly interesting because Phineas Gage became irreverent, right? Here's the most fascinating thing about the insula. As humans evolved, we started using the same rotten food circuitry to handle social and moral disgust. This is actually kind of important, but at a deeper level. When you hear about an unfair or gross violation of social rules, your insula fires exactly as if you smelled rotten meat. In Phineas Gage's case, his prefrontal cortex, which usually tells the insula how to interpret social situations, was gone. Many accounts of Gage describe him as becoming gross or profane in his language. He likely lost the ability to feel moral disgust about his own behavior. He might have still felt stomach disgust at a bad smell, But the social disgust that keeps us acting politely in public was no longer being regulated by his executive penthouse. So that's kind of interesting. Studies have shown that people who are more sensitive to rotten food also tend to be more morally righteous and also more likely to be conservative. It's because they get grossed out more easily, and so anything that they're not familiar with, they become grossed out more quickly than other people. And this leads to them being a little bit more conservative because they're less open to things that might be gross. Which, I mean, okay, fair enough. But yeah, so people who are more sensitive to bad smells are also more conservative, more politically conservative. Isn't that interesting? Interesting. It's because as Gemini says, it's the same part of the brain that's processing both ideas, right? Okay, next part we have to move to anger. All right, next I want to explore anger. Let's say one person is insulted by another. What happens in their brain and body in response? Anger is the brain's high arousal attack mode. While fear is designed to help you survive by escaping, anger is designed to help you survive by removing a threat through force or social dominance. When someone insults you, your brain perceives a social injury, and the response is as physical as if they had thrown a punch. Right? The amygdala hijacked the living room. The moment the insult is processed by the temporal lobe language, the amygdala sounds an immediate alarm. The threat detection. The amygdala doesn't distinguish between a physical threat and a threat to your status or ego. It interprets the insult as an attack. Right? So again, the same part of the brain responds, whether it's a physical attack or a social attack. The chemical trigger, it signals the hypothalamus to flood the body with adrenaline and norepinephrine, the brain's version of adrenaline. So the adrenaline goes into your body, the norepinephrine goes into your brain. The conflict in the penthouse, the frontal lobe. This is where the human experience of anger gets complicated. There is a tug of war happening in your forehead, right? The left prefrontal cortex usually becomes very active. Interestingly, while the right side is linked to withdrawal, fear, the left side is linked to approach behaviors. Anger makes you want to move towards the person. Right. So there's anger and fear. The orbital frontal cortex, this is like right above your eyes. This is the part of your brain responsible for checking your impulses. It's the part that says, wait, if I punch my boss, I'll lose my job. So on the one hand, you have your amygdala pushing your body to punch the guy, but then your logic part is also trying to hold you back. So like the two, like this part is trying to hold you back, and the part above is trying to make you punch the guy. The body, the pressure cooker. Anger produces the most intense physical arousal of almost any emotion. Your body is preparing for a physical fight. Right, your blood flow is redirected to the hands and arms, really. Not even your legs. This is why your fist clench. Your body is preparing to strike. Your heart rate increases sharply. You feel a thumping in your chest. Body temperature increases, hot-headed. Blood vessels in the face dilate, causing you to turn red. Your vocal cords tighten. Your voice becomes higher, louder, and more strained. I think we've all seen this happen before in our lives. But again, like you can see how the like Is it adrenaline? It was adrenaline, yeah. So the adrenaline kind of primes your body for these actions, right? For the anger chemicals, testosterone. Even in women, testosterone levels can spike during an angry confrontation, increasing the drive for dominance. Low serotonin. People with chronically low serotonin often have a shorter fuse because they lack the chemical brakes to slow down the amygdala's fire. So serotonin is the dampening chemical, right? It dampens your brain. And so people with low serotonin get angry more quickly because they lack the dampening. Fascinating. So the amygdala perceives a social threat the same way it perceives the physical threat. And then you pump the adrenaline out, and then the two parts of your prefrontal cortex try to decide whether you hit them or you don't. Oh yeah, and then this is interesting too, the Phineas Gage connection, right? The broken brakes. Phineas Gage is the ultimate case study in anger. Reports from his friends stated that after his accident, he was fitful, irreverent, indulging at times in the grossest profanity. Why? Because his orbital frontal cortex, the brakes, was physically destroyed. Right? So the right there, destroyed. His amygdala could still get angry. His hypothalamus could still pump adrenaline, but his prefrontal cortex could no longer say, "Stop, this is inappropriate." Gage lived in a state of unfiltered anger. He felt the impulse and acted on it immediately, because the bridge between his feeling brain and his thinking brain had been burnt down. Alright, so this is the final table. Interesting. Gemini kept track of the seven emotions, the big seven emotions, and it figured out that we finished all the emotions. But there is still like vigilance, anticipation, and interest. You know what? We can skip that. It doesn't really matter. All right, very cool. Very cool. So that goes through the whole range of human emotions, and we see how the brain responds. Like a lot of it, either you become more active or you become less active, right? I think the surprise one is the most interesting. The surprise one where the whole brain just resets and it stops everything else to focus on the thing that you're looking at. That's very cool. And of course, there's the happiness and love. It makes you relax. It makes you, uh, it rewards you, and it makes you relaxed. Versus like the fear and the anger, it dumps the adrenaline, it makes you more active, makes you more ready to act. So interesting, right? All right, so I'm gonna end this video here. What should we do next? I think I want to look at mental illnesses, and this might go on for quite a large number of videos. Go through the different like mental illnesses and just talk about how a person with a mental illness, how their brain is different from a normal person's. And so that and to explain why they are the way they are. Like if somebody has, let's say, anxiety issues, like why is it that they have anxiety issues? Like what is it about their brain that is different that causes them to have those issues? So I'm gonna like get a list of common mental illnesses, I guess, and then we'll go through those and explore how the brain can malfunction. All right, starting next time. See you there.